Okay, good afternoon. My name is Wei Lun. I'm part of the innovation team at Ecquaria. The innovation team basically has been building up machine learning capabilities for Ecquaria. Last year, you have seen a glimpse of how machine learning ML can be used to be integrated in the operations. Since then, we have developed new ML capabilities. I'd like to share with you these new capabilities and how they can further transform your operations. So I'd like to just first give a quick overview on what ML is about. For those who have attended last year's seminar, this will be a recap on what is ML about. So the essence of ML is encapsulated nicely in this equation over here. ML is about using math formulas to discover underlying patterns from data, and then to use these underlying patterns to make recommendations. The relationship between math formulas and data in machine learning is just like the relationship between a car and a fuel. One cannot work without the other. Without fuel, a car cannot function as a mode of transportation. Similarly, even the most sophisticated ML algorithms will not be able to give you recommendations without data. So in any ML solution that we propose, we envision working very closely with the agencies. Ecquaria will provide our machine learning expertise, and agencies will provide your data and domain knowledge so that you can build the best possible solution. And how we'll deliver our solution is through our product, Ecquaria Machine Learning, also known as EML. EML is a module under our flagship product, EGP. Over the years, we have used EGP to build up many IT systems for many agencies. Now, with EML, we'll be able to empower agencies with ML capabilities. And how we foresee ML can be mostly incorporated is in this manner. Many systems that we built adopt this workflow you can see over here. So you'll first start off with a citizen making an online application. Once it's submitted, the officer at the back end will be able to view the submission online, and then the officer will then make a decision on the submission. And this decision is either a simple approve or reject decision. Where EML can come in is to make a recommendation at this point over here. So you can observe that EML is here to assist the officer by giving a recommendation. The final decision maker is still the officer. So we're only here to help out the officer and not to replace the officer with EML. And how we build a model is through this process over here. The first step is to identify a problem. So the problem just now is about making recommendations, and I'll tend to make it a habit to phrase it into a question so that I know clearly what I want the model to answer. So in this case, I phrase it into this question over here. Should this licensing renewal application be approved or rejected? So I know my model, what my model to do. My model to tell me is approve or reject. So now I've identified the problem. Next step is to find past data. So past data in this case is referring to all the past submissions that have already been approved or rejected. So I'll gather all the past submissions and then put them in a table over here. Each row represents one past submission, and each column represents one form field. So now I've gathered all the past data. I need to carefully select the data that I want to use for my machine learning model. So I will choose only the license type, major incidents, and demerit points fields, and then ignore the date column, because the date should not affect my decision to approve or reject the application. Doesn't mean that I submit the same application yesterday, I approve it, then the same application submit today, I reject it. So date is not a factor in the application, I ignore it for my training of my machine learning model. And this leads to the next step, which is to train a machine learning model. To train a model is basically to scan through the data set. One scan of the dataset is known as one iteration, and typically to build a machine learning model, it will take around 100 to 1000 iterations. Whether it's 100 or 1000 depends on the size of the dataset I have. And once all the iterations are done, that means I can deploy the model to answer this question, and the output of the model will be something like this. This licensing renewal application should be approved. So what is this model that I've been talking about? It is a common term in the machine learning industry. You may have heard of it, but you may not know exactly what is it about. Same thing for algorithm. Another common term, but you might not know what is it. And so what is the relationship between algorithm and model? So the answer to all these questions is actually very simple. Algorithm and model, both of them, essentially, they are mathematical formulas. Algorithm follows a generic template, y equals ax plus b. A model has more specific numbers, y equals 2x plus 8. How these specific numbers 2 and 8 are derived is by training an algorithm through all the data. So what is going on in the training process just now is this. At every iteration, the numbers will be continuously adjusted. you keep on adjusting until you can best fit the data set. So once I found the best set of numbers, the model that I've been talking about is this model over here. So let me give you a graphic visualization of what's going on. So the x-axis is the training attributes, y-axis is the target that I'm trying to recommend, and then the blue dots here are all the data points. So what the algorithm is trying to do is to keep on adjusting this red line here until you can best fit the model. And the best fit line is found at iteration number 28. And this red line is basically the model that I can use to make a recommendation. So a new data point comes in, 2.78, then I can make a recommendation 12.01. So the interesting thing about this graph is that this point that I'm recommending, it is not part of the original data set. So this is where the beauty of machine learning comes in. I'm using only a subset of the data set I have to discover the pattern of the whole universe. And of course, the algorithms we use in EML, they are not as simple as y equals ax plus b. You've probably seen them in Emaths in secondary school. We use more sophisticated algorithms such as all this to solve different types of problem categories. And we're also able to use different data types. So last year, you have seen something about structured data and classification. So this year, we'll show you something different and hopefully more interesting. We'll show you something about finding similar items. We have moved beyond doing only structured data. We are now able to do data types such as text. Text will mean things like the text area fields in your application forms or even documents. I'm sure many of the agencies have such data types, so hopefully you'll take away something interesting from finding similar text. And also as an added bonus, if your agency also deals with images, you'll also be more than happy enough to handle these images for you and see what type of problems we can solve with machine learning. So that's the end of the recap of what machine learning is about. Let me go and dig deeper into the details of finding similar text. And how I will explain finding similar text is through this problem statement over here. As a movie viewer, I want an ML engine to recommend to me 10 movies most similar to my target movie based on movie descriptions. So I chose this problem statement to be in line with our unofficial theme of the seminar. So in case you haven't realized, our unofficial theme of the seminar is about pop culture. So that's why my colleagues made references to Spider-Man, Superman, references to Titanic, Jessie J, Leonardo DiCaprio. So now I'll continue from where they left off and recommend to you some movies to watch. Okay, so pictoriality is what is going on in the problem statement just now. So I have a target movie, in this case Star Wars A New Hope, and then I have a description of the Star Wars A New Hope movie. And what I want the machine learning model to do is to use this description to find similar movies out of a database of 46,000 movies. And out of these 46,000 movies, I want the machine learning model to tell me, out of these 46,000, which are the top 10 most similar movies to Star Wars A New Hope. And is there any difference? Okay, sorry. One thing I want to emphasize is that I'm only using the movie description themselves to train the machine learning model and totally ignore the title. Because I don't think the title is very useful in telling me the similarity of the movies. Case in point is these two movies over here. I have Iron Man and Iron Lady. They are very similar movie titles, but they are totally different movies. Iron Man is about a superhero, but Iron Lady is not about Iron Man's wife. Iron Lady is about Margaret Thatcher. So you can see from this example, similar titles don't mean similar movies. So I totally ignore the titles, and then I'm finding similar movies purely based on the movie description itself. And so the machine learning process actually broadly remains the same. You take on these 4 steps. First, identify a problem, which is this question over here. Next, find past data, which is all the 46,000 movies. Train a model, scan through a data set repeatedly, and then finally deploy the model to tell me which are the top 10 most similar movies. So broadly, machine learning process remains the same. The key difference is that I need to do something about this bunch of text before I can train a machine learning model. I need to convert this text into a suitable format to train a machine learning model, and that suitable format is in the form of numbers, not just any random numbers. I need to convert them into meaningful numbers that represent each movie accurately. And how I convert all those movies into numbers is through this natural language processing algorithm, NLP algorithm known as transformers. So I understand it can look a bit intimidating, so I just want to highlight a few interesting points. So the first point is that you can notice this term called feed-forward over here. Feed-forward is actually a neural network. On its own, it will be able to handle structured data. But if I want to handle chunks of text, paragraphs of text, then I have to need to build something more sophisticated on top of it. I'll use feedforward to build layers such as encoder, build layers such as decoders, and then chain all these encoders and decoders together to form this thing called a transformer. So what exactly does an encoder do? An encoder will try to encode the text into a knowledge base that's understandable by the transformer algorithm. The decoder will serve as some kind of check and balance. The decoder will make sure that whatever is being built up in the knowledge base is easily generalizable across the entire data set and not just one or two paragraphs. And you can notice that in this network, there is two encoders and two decoders. In a real architecture, there might be even more encoders and more decoders because they are there to handle sequences of words. Sequences of words are very important in any paragraph because you can have two paragraphs, exactly the same words, but you put them in a different sequence, it can mean totally different things. Case in point, these two sets of words over here. I have set 1, I have these 3 sentences, I read it in this order, I get a certain meaning. But once it comes to set 2, all I need to do is just swap sentence 1 and 3, and then read it in this manner. I get a totally different meaning out of it. So you can see that sequences of words in a paragraph matter, and how the transformer algorithm handles this is through a series of encoders and decoders. The encoders and decoders will remember the sequences of words and then process them accordingly. So let's take a look at some of the similar movies that are similar to Star Wars: A New Hope. To make it a bit more interesting, I will not review the movie title straight away. I will review the descriptions one by one. You can try to read the description and try to guess the movie for yourself and see whether or not it is really similar to Star Wars: A New Hope. Okay, so let me begin. So movie 1, I understand maybe some of you can't read it that clearly, so I'll just give a summary of description. So movie 1 is about Anakin Skywalker and Obi-Wan Kenobi. In this movie, they are both still Jedi Knights, so that's a big clue as to what this movie is. Movie 2, spoiler alert, Anakin Skywalker becomes Darth Vader in this movie. Movie 3, there's Luke Skywalker trying to learn from Yoda the ways of the Force. Movie 4, you have Luke Skywalker trying to rescue his friends. Movie 5, Luke Skywalker and Han Solo want to rescue Chewbacca. Okay, this movie is really something I never really even heard of. If you know what this movie is, you're really a big fan of this movie franchise. Movie 6, this happens 30 years after some big events happening in the Galactic Empire, so another big hint as to what this movie is. Movie 7, Anakin Skywalker is in this movie as well, but then he's only a young slave, a young boy. Movie 8, you have once again Anakin and Obi-Wan trying to rescue Jabba the Hutt's son. And movie 9, you have no major characters, just a rogue band of resistance fighters trying to steal the Death Star plans. And the last movie, you have Rey trying to learn from Luke Skywalker. So actually, if you are familiar with the Star Wars movie franchise, you realize that all the similar movies are from Star Wars. So when I was carrying out this similarity exercise, I didn't realize that there can be 10 Star Wars movies to be found. Because I know Star Wars, there's episode 1 to episode 9. Then episode 9 only comes out at the end of the year. So in the database now, there's only episode 1 to 8. But once I throw in spin-offs such as Rogue One and even holiday specials, I really have 10 similar movies that can be found by the model that are similar to Star Wars: A New Hope. And if I want to build a model to find similar movies, I do want the model to give me all 10 Star Wars movies as similar to Star Wars: A New Hope. Because Star Wars, all the movies in the Star Wars franchise, they are all of similar nature. They're all about science fiction. They're all about space. And so it is really encouraging to be able to see the model return me all 10 Star Wars movies as similar to Star Wars: A New Hope. You can take a look again at the descriptions. You can notice that there's really no fixed format as to how you want to describe the Star Wars movies. You don't necessarily have to start with a character like Luke Skywalker or Anakin Skywalker. You can just really write it in any way you want. You can start with the Galaxy, you can start with the Republic. But because they are all describing Star Wars movies, there are underlying patterns that the machine learning model is able to pick up and then identify all these movies as similar to Star Wars: A New Hope. So this is the end of the results for Star Wars. If you intend to catch Star Wars Episode 9 at the end of the year, you can thank me in advance for giving you an overview of all the Star Wars movies that have been shown so far. Okay, so now let me move on to the demonstration. The demonstration, I will go through this problem statement. As a new judiciary officer, I want an ML engine to recommend to me similar judgments based on the judgments I have found so I can have more reference materials for a case that I'm working on. So I'd like to just emphasize that even though this is about the judiciary sector, the techniques that you see later on in the demonstration can be easily applied to any documents, not just necessarily judiciary sector documents. So let me switch over to the demonstration. Okay, so as I'm going through the demonstration, you can take a look at the second screen to see the steps. So let me try and set up the. Okay, so the demo is there now. So let me go through with you step by step what the demo is about. So first step, the judiciary officer finds a useful judgment. So in this case, the judgment is a judgment about drugs. And the judiciary officer wants to find similar judgments to this judgment. He wants to find similar judgments to a database of around 6,000 judgments. It will be too manually tedious for him to comb through all 6,000 to find out what is similar. So he like to use ML to find similar judgments. So this leads me to step 2. The officer will click on find similar text. And so what is happening is that EML behind the scenes in step 3, it will look through the judgment and then split the judgment accordingly into paragraphs. For each paragraph, EML will behind the scenes try to find from other judgments paragraphs that are similar to this paragraph over here. So let me just skip to step 5 by showing you a preloaded result. So in this case, all the results are loaded. So the officer can go and take a look at what is being deemed as similar to each of the paragraphs in the judgment. So let me show you an example. Let's say the first paragraph. I click on view results. So this is the paragraph that the EML is trying to find similar paragraphs to. So this paragraph over here mentions about the accused, 25-year-old male, and then the offense that's been committed. And that's, in this case, the Misuse of Drug Act, MDA. And you can see that all the paragraphs, they are being identified as similar. They all mention the accused, the age of the accused, and then the offense committed. Not just any other offense, but Misuse of Drugs Act. So this applies to all the paragraphs you can see over here. So even though it's a successful implementation of EML finding similar paragraphs, it might not be very useful for officer trying to find reference materials because this is just a generic introductory paragraph. It might not be very useful as a reference material. So let me take a look at another paragraph. So let me share with you this paragraph over here. So this is quite a long paragraph, but the key sentence here is that the indicative starting point within this range should be identified based on the weight of drugs involved. So what this sentence is trying to say is that whatever sentence that is being meted out by the judge, the weight of the drugs plays a part in determining what is the sentence like. So in all the similar paragraphs, they all do mention something about the quantity of drugs, as well as the sentence, and even the sentencing range 26 to 29 years. In this case, same thing, quantity of drugs you can see, and then another sentence of 20 and 30 years of imprisonment. Okay, so that's the end of the demo for finding similar text. I'll now hand over to my innovation team colleague Wei Pin to talk about finding similar images.
Right. Alright, thanks Raylan for showing us on how machine learning can be used to find similarities in text. Now I'll go on to the next domain of images. So finding similarities in images for humans is something that's is very easy. We look at the image, we can see what the image is, and we can see which other images are similar. So let's take a look at this simple example here. Let's say that we were to find the two most similar pairs among these images. Immediately off the bat, we can see that at the top right, there are these two logos. Antler Ranch is basically the same logo, just that one is a bit more zoomed in than the other. And then we can also see, there are two Apple logos here. One is the black version, black and white version. One is the multicolored version. So this one, immediately we can see. It's very easy. But keep in mind, this one is only about 6 by 5. It's about 30 images only. What if we have more and more and more images? So now let's say we have to choose a random image from here. Let's say the one at the top left. And then out of this, we are supposed to find the 5 most similar images to this image at the top left, and also rank it in order from 1 to 5. Now then this one, it's not so straightforward anymore. We probably could do it, but it might take, half an hour, okay, maybe 10 minutes if your visual capabilities are fantastic. So this is how machine learning can come in and help in this problem of finding similar images. So for machine learning, the problem statement can be viewed as follows. We have a target logo for finding similar logos. In this case, it's this A over here. Then the machine learning model scans through a database of logos. In our case, our database contains about 6,000 logos. And then after that, the machine learning model will recommend, like, let's say, 20 most similar logos. 20 is just an arbitrary number. Yeah, but it'll recommend the most similar logos to this target logo. So let's take a closer look at these similar images. And then from this, we can clearly see that there are two principles of image similarity utilized by the machine learning model. Number one is that the machine learning model, they identify similarities in the overall shape of the logo. So previously our target logo was an A, it has a triangle shape. So all of the logos here, they have a similar triangle shape. And the next principle is it ignores differences in color. So regardless of whether the logo is black, whether the logo is multicolored, whether the background is black, background is white, it all doesn't matter. It's all treated as equal. So these are the two principles of image similarity, shape and ignores color differences. So now how this is done, you can go back to our familiar 4-step process that was previously mentioned by William just now. So first we identify the problem. In this case, our problem will be which logos are most similar to this application's logo. Then we find past data. Past data in this context will be logos. Yeah, we train the model, scan through the data as always, and then finally we deploy the model. So after the model is deployed into a production environment, then the output of the model will be something like, these 20 logos are most similar to this application's logo. But how the machine learning model processes these images, of course, it's not like humans. We take the image as it is. Machine learning models, they are all based on math formulas. So because it's a math formula, we have to convert all of this to a numerical representation. So this process is done via a tool called a Convolutional Neural Network, or ConvNet. So a convolutional neural network sounds strange, but I'll just give a very high-level overview of what it is and how it processes images. So it's simply an artificial neural network that is especially useful for image processing, image classification, image recognition. So this ConvNet, how it works is that it mimics how a human brain works. In that, when you pass it an image, it will try to extract the important features from the image. So for example, let's just take a simple example. For example, let's just take this projector over here. So how do we humans know that this is a projector? You get it? Okay. It's this white rectangle, it emits some light over there, and then it has some cables that's connected to a power supply. So these are the important features that we're extracting from this projector. And then we note it down, and then based on our past history of how projectors look like, we know that we conclude this is a projector. So similarly, a machine learning model, they will look at the image bit by bit, they extract the important features from this input image. And then also this ConvNet, it also reduces the size of the input to be processed. So for this, I will delve into it a bit more later. So let's walk through this ConvNet process by using a simple example. So here we have the old school multicolored Apple logo. In our database, all our logos have these dimensions, 148 by 148. And then because this logo is a multicolored logo, there are 3 layers of RGB. So simply, we can do some basic math. We can do 148 by 148 times 3 equals to about 65,000 attributes. So in other words, this image can be represented in the 65712 attributes. So of course, our goal is to convert images to numbers. So of course, we can use these 65,000 attributes and input it into the ConvNet as training. But we do not do this for 2 reasons. Number one, 65,000 attributes is a very raw form of the image. There's no compression whatsoever. So this is just for one image. Imagine if there's thousands and millions of images, the processing time will be significant. Then number two is that 65,000 attributes, the full taking all 65,000 attributes might not actually be the best representation of the input image. So bear with me here, I'll delve more into that as well. So what the Convet does is that it takes in this input image, the 65,000 attributes, and it converts it into, it reduces it into just 8192 attributes. So immediately some people might think, 65,000 down to 8,000, that's the 8 times 8-fold reduction. Is it possible for the 8,192 attributes to accurately capture all of the information of the image without any information loss? So I'll try to prove to you that actually this 8,000 attributes forms a better representation of the image compared to the full raw version of 65,000 attributes. Right. So this example, simple example will illustrate that. Here we have two logos. For human, immediately we can see both are checkerboards. Both are the same thing. 100%, okay, maybe not 100%, 99% similarity. But then for a machine, these two images are completely different. Because when you inspect this more closely, you can see that what is black in checkerboard 1 is actually white in checkerboard 2. So if a machine processes it pixel by pixel, all of these pixels are completely different from one another. And then it'll say 0% similarity. But then what the ConvNet does is that it takes in the 65,000 attributes, it converts it into the aggregated form of 8,000 attributes. So the machine without ConvNet, if you take all of the attributes, you'll see these two images as different. Whereas if it's the aggregated 8,000 attributes, they will be able to see these images as similar. Okay, so now let's just show some sample results of logo comparison. So over here, how you read this chart is that the target logo will be the one at the top left, and then after that, it'll be ranked in order in this like left to right zigzag fashion. So here our target logo is the aforementioned A, and then you can see all of these logos follow the two principles mentioned earlier of follow the shape. Here all of them have a triangular-ish shape, and then color differences are ignored. So the next example, we have our multicolored Apple logo again. And then here we see the most similar logo that's found is the new style black and white Apple logo, which makes sense. And you can see that it clearly follows the shape principle as well. The target logo here, Apple, the right side has an indent to mimic someone taking a bite of the apple. So this indent on the right side can be viewed in many of the other similar logos. For example, the one over here, and then the one over here, the bottom left, as well as the bottom right, sort of. There's the indentation on the right side. Then the next example, our target image here is this running man holding a giant pencil in his right hand, and then with some words encircling it. The most similar image found here will be the running man with the giant pencil without the words around it. And then the second most similar is what looks to be a running man as well, holding a giant spear. And for this second example, you can see that orientation does not matter. Target logo, the running man is running to our right. In this one, the running man is running to the left. And then when you look at the bottom row, you see more instances of this as well. These two, I don't know, men. This one looks like some angel with wings, that they're both running to the left. But orientation, run left, right, up, down, it all doesn't matter. Alright, so that's just some sample results. Now I'll do a short demonstration of finding similar images in the EML platform.
You're talking about the problem statement?
Oh,
That's right.
Okay. So in this case, in our demonstration, our problem statement, you can see on the second screen. As an application officer, I want an ML engine to recommend to me 20 logos that are most similar to the logo in the current application that I'm handling. Yeah. So in this case, we have this logo that's uploaded. We have Dockers chocolates. And then by default, we have this, it will take the entire image to compare for similarity comparison. Yeah, so let's click on it. When you click on it, you see the output images of the most similar symbols found by this will follow a similar shape. So you can see all of them have this circle at the circle as a logo, and then some words at the bottom. All of it roughly the same. Ecquaria is here as well, featured a couple of times. But then let's say as an application officer, you don't really want the words, but you want to focus on the B, because the B is the main part of the logo. So there'll be this cropping as a cropping image tool. So let's just crop out this B portion, and we do the similarity check. So we can see that when we just crop out the B portion of it, just the logo, the circular logo, now the output images by the model is different. Now the image, the bottom text part is largely ignored. So the most similar ones you found are all with in the circular shape. Circular shape. We see that this one appears as well. This one was previously the number one most similar image. So it is now, it's still found, but it's relegated to position 15. And then finally, of course, if you want to just crop the text part, we can do it as well. Yeah, so if you just crop the text part, you see logically it will one of the output just text. But I don't think this will be very useful to the application of this. I mean, this is just for demonstration purposes. But the main thing here, of course, as an officer, you want to compare the B portion. All right. So I will just go back quickly to our slides. Sorry, mic. Sorry, mic. Oh, okay. I found my mic. Yeah. Ready?
I think just start again.
Right. So now we talked about how machine learning can be used to find similar text, find similar images. It's all fine and dandy. But let's bring it all back to the pertinent question at hand. How can machine learning be used to help to solve some use cases in the government context? So I'll just bring you through some of the possible use cases for machine learning for the cases that we have mentioned. So finding similar text, as mentioned previously, easy use case is to find similar judgments to some reference judgment. So this can be useful to a junior judge, junior judicial officer, or maybe just some new court officer, or just other stuff in the court. Maybe it'll be useful. And then this also applies for any other things that involve some text processing. So for example, as an officer that's processing some inspections, that inspections you will have let's have some lengthy documents. Some junior officer, they want to have some past reference to past inspections conducted. This can be used to pull up all the past inspections so that they can compare and use as reference to guide them in their actions. So next, for finding similar images, the use case would be in a trademark context. So for example, if you're processing trademarks, someone submits a new logo, you want to verify that this logo is not already it doesn't really exist. Otherwise, to prevent any infringement of copyright laws or whatever. So this will allow officers to ensure that the new proposed logo is not a duplicate of, or may not just duplicate, or is not too close of a resemblance to any existing logo. So of course, we are not restricted to just finding similarities. For example, in the text context, finding similar text entails the NLP part. We can combine this natural language processing portion with other methods of like classification that was talked about in the previous seminar. So we can do classification for documents. Let's say you have a whole chunk of documents, you want to classify them into some categories. This can be done using machine learning. Number one, can categorize court judgments by the type of crime. You have a whole list, usually theft, drugs, crime, whatever. Maybe this will be good for some internal sorting or for some officers to use it. And then for the waste reduction context, can classify all the improvement plans, maybe just from like 10 years ago until now, you can categorize them into for which campaigns they were used in. Reduce, reuse, recycle, or whatever other marketing campaigns they were embarked on. And maybe categorizing grants or study awards or scholarships by application status. These are past history, you can see clearly segregate them into which ones were awarded, which are not awarded, which ones selected for interview, this one maybe stage 1, stage 2, or etc. Or simply categorize feedbacks by the sentiment, positive, negative. And also just categorize any whatever reports that were done, reports by the outcome, pass, fail, further action, or just generic action 1, action 2, action 3, action 4. Alright, so that concludes my machine learning portion.